Good morning, everyone. So we are here today for an introduction to containers and Kubernetes, specifically in the context of machine learning operations. For those of you for whom it's not your first Open Cloudification webinar, you might already know me. My name is Merlin. I'm a researcher at IMEC and I teach at Ghent University. And I also work on a lot of open source software and standards. Today, I'll first start with just giving a quick intro for what Open Cloudification itself is, this project. Then I'll start with just situating the context of machine learning operations. Why does machine learning operations exist? Why is it important for machine learning engineers to do it? And then I'll introduce Docker and Kubernetes from the standpoint of what benefits does it have for machine learning operations. So Open Cloudification is a project funded by the Flemish government, where we basically help companies figure out how to use open source software in order to improve their cloud, edge, and IoT deployments. And so as part of that project, LSEC is one of the partners of our project next to us at IMEC. I can definitely recommend to go to our website where we have a lot of resources showing the cloud native landscape and helping you to navigate that landscape and helping you to figure out which tools are important and useful for you. It is a project that we do in collaboration, as I said before, with LSEC, but also with the Beacon, and then from our side, IMEC. We do a whole bunch of webinars. We have some white papers. We also have a sandbox environment that you, as basically a customer of this project, can use in order to test out cloud native and open source technologies. And basically, the idea is that we help you navigate this gigantic cloud native computing foundation landscape. There's a lot of these tools out there. We have a lot of experience with a lot of these tools, and we can help you figure out how to use these tools. So if you're interested in this knowledge, please subscribe for our monthly webinars, and also feel free to contact us. We can help you with specific one-on-one sessions if you have more specific questions. Now, about machine learning operations. What a machine learning development model should look like is basically that as a machine learning engineer, you're designing what your application and what the functionality should look like. You develop your model, you put your model into production, and then there you have your product. And then you can use the experience you get from running your model in production to then further develop your model or maybe redesign certain things. But the issue is that moving from this model development to operations, this is a very complex and very unstructured handover in a lot of companies. Even though there's a lot of companies that have very good machine learning models that show their value in a test setting, it's sometimes very complicated to actually bring those models into production. And this really puts a big damper on the time to market. Basically, it requires during model development, it requires basically 90% of the time is often spent on actual glue coding to ensure that your model can work in a real world scenario. The goal of machine learning operations is to reduce this technical friction, to reduce the time to market, to get the model from an idea into production in the shortest possible time with as little risk as possible. There's a lot of shared principles that will take you a long way. Machine learning should be collaborative. The goal of machine learning operations is to be able to build machine learning models with multiple people or even with multiple teams. Your machine learning should be reproducible. Whatever works in your testing environment should also work in your production environment. It should be continuous. You should be able to use feedback loops from production to bring those into development and into design in order to keep continuously improving your model and your products. And they should be tested and monitored. Kubernetes and Docker, they basically help you solve these middle two steps. Machine learning should be reproducible and it should be continuous. It's basically, this lecture is about the handover and deployment from model development into operations. The solution is basically to hand over, to automate, to completely automate the handover from the dev to operations. And so the first part of that is containers. And I wanted to give you a little bit more of a big picture view of what containers are specifically and what problems they specifically solve. Because I think a lot of developers this day and age have some experience with containers, have some high level understanding of what containers do. But I want to make it clear that it's very clear what specific problems containers solve. Um, the name containers literally comes from shipping containers, and it is a very good analogy. So before shipping containers existed, basically all the cargo in a ship was put just in the cargo space. This was a very manual process by hand, and it meant that every different type of cargo needed to be handled differently. If you have barrels of oil, if you have sacks of flour, if you have basically tubs of water, you every type of cargo has a different way to handle it. And so some types of cargo had specialized cranes in order to handle that cargo, but a lot of cargo just was handled by hand. Um, each type of cargo required different handling, which is labor intensive, slow, and very hard to automate. And so shipping containers were basically the idea of, okay, instead of having to build human robots that can do everything by hand, we are just going to change the problem. Instead of creating a very complex solution for how to automate this loading of ships by hand, we are going to change the problem, basically put the trucks directly on the ship. Um, this is basically the person that invented shipping containers. He basically had the idea of, instead of having to manually load goods from a truck into a ship, why don't we just put the trucks on the ship? But then instead of having to also put the engine and the car on the ship, we just only put the backside of the truck where all the goods are stored on the ship. And so as you can see here, basically when you change the problem from, instead of having to manage everything by hand because everything is very different, by changing the problem into, okay, we now have a standardized unit of goods that all our automation can handle, you saw a lot of standardization and you saw specific cranes and specific automation infrastructure that was specifically built just to handle these shipping containers. And because of that, it was a lot more easy to automate everything. Docker containers, Linux containers, or containers in software development, they basically solve the exact same problem. Managing software, deploying software, configuring software is very difficult. And Docker containers are a standardized unit to package a piece of software in a way that makes it very easy to automate the entire lifecycle of this software. It's just the idea of we package software into standardized units for development, shipment, and production. It packages the code, the settings, and all its dependencies, and it runs completely isolated from the host operating system so that you know that once it runs in a container, it runs everywhere. And all your automation tools, they don't need to handle these complex applications anymore. Every single application looks exactly the same from the viewpoint of the automation system. A big enabler for this is the fact that containers isolate applications from each other. I do want to make it very clear though, when we talk about isolation in the context of Docker containers, we are talking about isolation as a convenience feature. Docker container isolation is not secure. You should not use this as a security feature. You should only use this as a convenience feature. If you need to actually securely isolate containers, then you need to switch to other technologies, such as virtual machine-based orchestrators like Kata containers. But yeah, the idea is that with a container, you install, remove all dependencies of an application in a single command, and the command is always the same regardless of which specific application it is. Docker containers are often compared to virtual machines because for a very long time, virtual machines were also just the unit of packaging software. The big advantage of Docker containers is that they are much smaller. They basically contain the bare bones dependencies necessary in order to run your application. And it runs natively. It has direct access to the hardware. It's a single application, while virtual machines, they are very big, they are virtualized, and they only have virtualized access to hardware. However, I put an asterisk on the point of direct access to hardware, and this asterisk is here in order to remind you that by default, containers are isolated from the operating system. So if your application needs access to hardware, for example, if your application needs access to a GPU or to AI accelerators embedded in the hardware, then you will need to poke some holes in this Docker container sandbox in order to give your application access to the underlying operating system. So let me just start with a Docker overview and also explain to you how do you poke these holes in the sandbox. So a typical Docker workflow basically works like this. You take a Docker file, which describes basically how to build your application, how to build the container for your application. You take that Docker file and you use that to build your Docker container. You push that container to a registry from the place where you want to run your application. You pull the image to that host operating system, and then you run that container from local image. And so you basically have three machines in this Docker flow. You have the place where the container gets built initially. This is often inside of your CI/CD pipelines. You get the place where you push the image to. Docker Hub is such a registry. And then you have the host where you actually run your containers. And so building Docker containers, it's basically using a Docker file. A Docker file is just a text file that contains the steps of instructions to build your Docker image. Important to note here is that Docker images almost always start from a base image such as a base Ubuntu image. Basically, whichever operating system your application runs on, that's the operating system that your Docker container should start from. And then you just run commands just like you would do in order to install them on your laptop or on another server manually. You run these commands as part of your Docker files, and these commands will run in order to build your application. And then you can also insert your own applications. And then this file, you give this file to Docker in order to actually build the Docker container. In a temporary container on your build machine, these instructions will be executed and the resulting image will be your Docker container. Important to note is that if you want persistent storage in a Docker container, you need to do some special things because by default, if your application writes to disk, it will write to the disk of your Docker container. So imagine this is just a virtual machine. When you write to disk, it will write to the disk of that virtual machine. And when that container disappears, all that data is gone. That is the first thing to remind yourself of. If you just write to the normal disk of the container, when the container is gone, all that data will be gone. But second of all, this is a virtualized file system. It has a lot of overhead because it's a layered file system. So if you need performance in your disk reads and writes, please do not write to the regular file system of the container itself. What you actually need to do is use volumes and mounts. These are two options for containers to store files on the host machine. The host machine storage is not virtualized, it's just the host storage. So if you store your files there, then first of all, when your container disappears, your files will not be gone. And second of all, you will get a lot better performance. It is recommended to isolate data from a container to retain the benefits of adopting containerization. Data management should be distinctly separate from the container lifecycle. A lot of machine learning MLOps frameworks already have a complete system for managing the lifecycle of your data. Well, you should just plug that into your Docker containers. The second thing I explained was that Docker containers are isolated from the host system, which means that by default, it doesn't have access to host GPUs or AI accelerators. If you want to use GPUs from inside Docker containers, then you need to tweak a few things. First of all, your host machine needs to have a Docker release, which is newer than or equal to the release 19.03, because at that point, the GPU functionality was added into the Docker release. Secondly, your host machine needs to have the NVIDIA CUDA driver installed, which is more or less logic. Like your host obviously needs the NVIDIA driver installed, but it also needs to have the NVIDIA container toolkit installed. This is basically what Docker then uses in order to use GPUs inside of Docker containers. Your container needs to also use a few changes. So you basically need to start from a base that is GPU enabled. So earlier I said, if your application runs on Ubuntu, you should be able to just start from the Ubuntu image. Well, in this case, if you want to use NVIDIA GPUs, you should start from a base that has these NVIDIA drivers built in. Some good bases are NVIDIA/CUDA or NVIDIA/TensorFlow. These are two bases based on Ubuntu that already have the NVIDIA guest drivers built in. And you need to start your containers with --GPUs space all, because this basically gives your containers access to the GPUs. And when you do all this, then you can run your machine learning models inside of the Docker container without any significant overhead. Because these containers, they directly contact the GPU on your host system. They get a direct line to the GPU on your host system. So I just want to explain a little bit about the terminology that I'm using. I'm always talking about Docker containers, but when I'm talking about Docker containers, I actually mean OCI containers. Every layer of the stack of Docker containers is standardized as part of the Open Container Initiative. And so even though Kubernetes, for example, Kubernetes in the backend, it doesn't really use Docker. It uses some of the low-level software that is used to build Docker, but it doesn't use Docker itself. But it can still run Docker containers because these are just standardized OCI containers. And so in almost every single example, Docker and OCI are interchangeable terms. That's why I just use Docker containers, because the Docker name is much more widely known. Even though Docker actually refers to a very specific piece of software that is mostly used on guest laptops. That's mostly used on developer machines. Most of the time when you run Docker containers on servers, the Docker tool is not actually used anymore. So the second part of this lecture is about Kubernetes. Kubernetes is a container orchestrator. It's an open source system for automating deployment, scaling, and management of containerized applications. So go back to the start of this webinar, where I explained what the point is of containers. The point of containers is to give your automation system a standardized unit in order to automate the deployment of containers, of applications. And basically, Kubernetes is this automation tool. So if you just use Docker containers without Kubernetes, even though you might already get some of the benefits, for example, to have more reproducibility and more robustness, in the sense that you basically know that when it runs on a dev machine, it will also run in production. The real benefit of Docker containers comes when you pair Docker containers with a container orchestrator like Kubernetes. The problem is basically the moment your company gets to a certain scale, you have many servers, many containers running on these servers. You have continuous change applications crashing, new deployments, updates, auto scaling. And so the solution is to automate everything using a container orchestration framework. This is both about provisioning, deployment, scaling up and down, and networking itself. Important to note here is that this is done in a declarative manner. This is really key because this really enables container orchestrators. In my opinion, this enables it to be used by people who are not system administrators. This really reduces the barrier of entry to use container orchestration systems. The idea is that you describe the state you want the system to be in, and then the system continuously tries to reach that state. So the idea of the desired state model is basically that in your Kubernetes YAML file, you describe this is the final situation I want, this is the final state I want my application to be in. I want these containers to be deployed in that location, and I want them to run in this scaled manner. And then Kubernetes will figure out like, okay, so how many instances of your application are running at the moment? What do I need to do in order to bring that application into the desired state? And then it will take those actions. So you, as a machine learning engineer, you don't need to think about, okay, which specific Linux commands do I need to execute first in order to figure out what is already running, and then in order to bring, to change what is running in order to bring it into the state I want. You just explain the desired state. In Kubernetes, this is basically you describe your application in a YAML file using Kubernetes objects. And then the Kubernetes control plane, the controllers inside of Kubernetes, they will look at this desired state and update the containers and volumes and networking infrastructure in order to deploy the application that you just requested. So why don't we use scripts? Why don't we just use scripts in order to automate containerization? We see that a bunch of companies first use scripts because Kubernetes seems like this behemoth, this complex system that a lot of people are scared of. And the reason why we don't use scripts is because of what we call this automation fear cycle. The problem is that after you initially ran your script in order to deploy your application, you see that some stuff is still wrongly configured, and you make these changes outside of your automation tool. But that means that your servers are inconsistent with what your automation tool expects your servers to be in. So you're afraid to rerun your automation tool because maybe your automation tool, your script, maybe it will rewrite those manual changes that you just did in order to make your application work. So you'd make more changes outside of your automation tool, so your servers are more inconsistent, so you're more afraid to run your automation tool. And what we actually see is that companies that use scripts for automation, they basically just use these scripts to deploy the application the first time, and then they never touch these scripts anymore. The whole problem with scripts is how to do continuous monitoring and resolution of issues. This is what these desired state models of Kubernetes really excel in. If issues happen during provisioning or during scaling, or if an outage happens, or if an application crashes, then your automation system, if it uses desired state, it will see what is happening and it will update your system in order to get it back into the state that you want. As an example, last year, our data center at Ghent University went offline for a few hours because a crane basically sailed against the electricity network and took down the electricity network in the entire city where our data center is located. That recovering from that would be a big issue if it were not from Kubernetes. After our servers came back online, after the electricity was restored, Kubernetes basically started looking at all our servers, looked at, okay, what is running on all these servers? Then it looked at our previous desired state model, what we previously requested as system administrators, and then it brought everything back online. It brought everything back into the state that we wanted it to be without requiring any manual intervention from us. And so this really saved us weeks of rebuilding our infrastructure because the system just did it for us. So let's take a little bit more of a deeper dive into Kubernetes and how it works. Important to know about the Kubernetes architecture is that you basically have the control plane. The control plane, this often runs separately from your actual workloads, your actual applications that you want to deploy in Kubernetes. And this control plane, this is basically the responsibility of the control plane is to see what you request and then deploy what you requested. But then if you want to deploy applications, you need to use Kubernetes pods. A Kubernetes pod is the most basic Kubernetes object. It's one or more containers with shared volumes, shared network. Basically, a Kubernetes pod is just a container. But because sometimes, as an implementation detail, you might need multiple containers to act as if they are a single container, Kubernetes pods make that possible. Important to note is that pods are ephemeral. This means that they can be destroyed at any time and do not have fixed network addresses. Kubernetes will kill your pods as it sees fit. If, for example, Kubernetes needs to balance the load and it sees that currently the load is unbalanced, it can just remove pods in order to balance the load. If you want to restart your application and you ask Kubernetes to restart your application, what Kubernetes will do is just it will remove a pod completely and it will create a new pod. So very important. Do not store important data in RAM without a backup on disk. Do not depend on the IP address of a pod, and do not write important data to the disk of that pod, to the disk of those containers. This means that you might need to change your application architecture to fit into Kubernetes. Basically, your application should be able to handle being killed and then restart it somewhere else. If that is a problem, then you need to change your application before you run it inside of Kubernetes. If that is a problem, then you need to first use virtual machines before you can start using Kubernetes. But then the question is obviously like if Kubernetes will just kill any pod that I create without even creating a new pod or something, then how do I ensure that my services keep running? Well, the answer to that are Kubernetes workloads. Kubernetes workloads define how something should run. These are higher level Kubernetes objects that manage pods. So, for example, a deployment and a replica set are for stateless applications like microservices. You explain there's multiple microservices that basically have the exact same functionality, so you combine them in a deployment. Um, a stateful set a stateful set is for stateful applications like databases. If your application uses persistent storage and that persistent storage basically stores important data, then you need to use a stateful set. The final type of workload are jobs and cron jobs. Jobs and cron jobs are for one-off processes such as nightly backups. A pod template inside of a workload defines what should run. So instead of creating pods directly as an engineer, what you actually should do are create deployments or stateful sets or jobs. And then Kubernetes will, based on the deployment, will create pods for you using the pod template that you add to that workload. Okay, so this is how you ensure that your application keeps running, even though pods can be killed. So how do you actually contact these services? Because each pod has a different IP address, but pods can constantly change. Services is basically the solution to that. A service is a long-lived network endpoint to contact multiple points. You can basically look at services as some sort of load balancer for pods. It's a static IP or a static DNS name that basically connects to a deployment or a stateful set or something else. There's three major service types, and these service types, they basically depend on how do you interact with this service. If you want your service only to be available to other applications running inside of the same Kubernetes cluster, then you can use a cluster IP service. Cluster IP service just gives an internal IP address to a group of pods. Node port. Node port is a useful service type for if you want to make services externally available so that applications outside or users outside of the Kubernetes cluster can still contact your service. And then load balancer is basically the fully fledged load balanced service type. So if you have a load balanced web service, for example, and you run that in Kubernetes, then it's best to use the load balancer service type in order to then make this service available to the outside from a single IP address. You expose workloads to the outside using cluster IP and the node port service. Cluster IP service exposes a service on is strictly internal virtual IP, while node port makes it available to the outside using a cluster IP service. Load balancers, well, they are load balancers. They're a single publicly addressable IP for your internal services. And then ingress. Ingress basically allows you to add additional configuration to this service. For example, if you have multiple domains running on top of the same IP address, that is where ingress comes in, and ingress will then route traffics to the correct backend applications based on which URL is used or which domain name is used. So then, I talked about storage. I talked about that Kubernetes also supports stateful applications. So how do you actually use these? What do you do with stateful application inside of Kubernetes? The whole idea of stateful applications is that they have somewhere to store their persistent storage. Pods themselves are very useful, but many workloads require exchanging data between containers or persisting some form of data. For this, Kubernetes offers volumes, which are temporary storage, persistent volumes, which is persistent storage, and persistent volume claims. They basically bind a persistent volume to a pod. And so, as the name implies, a persistent volume remains in your Kubernetes cluster and keeps existing, even when no pods are using it. And when a certain pod writes some data to a persistent volume, and that pod disappears, and then later a new pod appears, and it binds itself to the same persistent volume, and then reads the data, it will read the exact same data that the other pod wrote. Storage classes are basically a class of persistent volumes. So for example, if you want to make it possible for developers to create their own persistent volumes as they see fit, you can create a storage class that connects to maybe a network storage server, an NFS store, or a Ceph cluster in order to make it possible for users inside of Kubernetes to request storage from this storage server. Then the next question is, okay, you have these deployments. How do you actually manage entire applications? Because writing these Kubernetes YAML files by hand and then changing them every single time you want to change something in your application, it might become a little bit complex. The first step, the actual first step when you deploy applications as Kubernetes should be to just write a Kubernetes YAML file describing your application. But then when you want to go to like the second step of really automating application management, Helm is a great tool to do that. Helm is basically a package manager for Kubernetes, allowing developers to more easily package, configure, and deploy applications. And then with an application we mean basically a combination of multiple pods and services and persistent volume and other things. Helm basically allows you to manage all these things as a single application. The downside is that Helm is mostly used at day one operations. It's great at installing and upgrading software and software dependencies, configuring software deployments, and fetching software packages from repositories. But when you actually want to do things like running backups, running maintenance on your database, and things like that, that's where Helm is can't really help you anymore. When you need to automate those kind of things, then you need to basically go into the third step of managing applications on Kubernetes, which are operators. Operators are basically plugins to the Kubernetes control plane in order to add additional functionality into Kubernetes. By default, Kubernetes cannot deploy databases. It can only deploy pods. By default, Kubernetes cannot do a backup. It can only deploy pods. But using an operator, you can add additional functionality into Kubernetes, and you can make it possible for Kubernetes to do backups, to deploy databases, to manage very complex software. They are application-specific controllers that continuously monitor the state of the application and intervene where needed. Basically, the difference between Helm and a Kubernetes operator is that if you just want to install your application, then use Helm. If there's not a lot of customization involved, then use Helm. If you have very, very special customization, then use an operator. If this is your first interaction with Kubernetes, then use Helm. If you have a lot of experience, multiple years of experience with running applications inside of Kubernetes, then an operator might be more useful to you. So operators basically are extensions to this Kubernetes control plane. They look at the requests of the user, and such a request might be, give me a database, or do a a backup of this server. And then they change the pods and volumes and containers in order to perform that work. So there's a lot of existing operators, which basically allows you to reuse codified operational knowledge of, for example, how to do encrypted virtualized storage. Rook is an operator that completely manages virtualized storage for you. How to do security policies. You do that with the open policy agent operator. How to do zero trust communication between your services. Well, the linkerd operator will do that for you. And so obviously, as a machine learning engineer, there's a lot of operators that can really help you take better advantage of Kubernetes. KubeArray is a great example of this. It is basically a way to build and scale machine learning and Python applications on top of Kubernetes. It integrates with third-party things like MLflow, Feast, Ray. It integrates into persistent storage and really allows you to manage your machine learning pipelines inside of Kubernetes. Kubeflow is another great example. Kubeflow is really an end-to-end suite for AI and machine learning on Kubernetes. And so you install Kubeflow as an operator, as a plugin to the Kubernetes control plane. And once it's installed, you have much more high-level concepts in order to deploy on Kubernetes. It's not just I'm deploying pods, but you can really deploy machine learning pipelines. You can use it to develop, train, test, stage, serve, and archive your machine learning models on top of Kubernetes. If you want more information about how to use Kubernetes, how to do machine learning operations on top of Kubernetes, the first thing I can definitely recommend is to go to the Kubernetes website because it has a lot of starting content. The Cloud Native Compute Foundation also provides a lot of trainings. Kubernetes has a great website with a lot of documentation and examples. It also has communication channels with thousands and tens of thousands of users that will, and a lot of them will be very happy to try to help you. But if you need more personalized help, if there are certain topics that you are interested in, then you can always contact us. This is my email address. You can always contact us and we can help you as part of this open cloudification project, or we can maybe organize webinars or workshops that are tailored to your specific needs. So if there are any questions, I am happy to look at your questions now. Let me open the chat here. Okay, so I don't immediately see any questions. I want to reiterate, if you want personal help, if you want to give suggestions for our next webinars or workshops, please contact me, send me an email, or follow me on LinkedIn to stay up to date about our upcoming webinars.